All right. How was everyone's weekend? Not good? Oh my God. Don't tell us more, please. Okay. That's sad to hear. I hope that at least some of you had a good weekend. Anyhow, we're back. Continue our discussion of the seventh worksheet. And we were discussing this question of what are the update equations for double expected SARSA with an epsilon greedy target policy. And we got to the point where we had the update equations for double Q learning. We discussed the idea behind double Q learning. And now it's time to apply our knowledge of what this idea of double learning is to expected SARSA. So let's do that. So to solve this problem, we have to know a few things. We discussed double Q learning, the idea of double learning. The next thing to know is expected SARSA and how it updates things. And we have discussed this. And I just write down what the update equations are going to be for expected SARSA. So we're updating action values. We are processing state action, reward, next state, next action. Well, not next action, because that is expected SARSA. So the data is just going to be ST, AT, RT plus 1, and ST plus 1. And the next action value only changed at the state action pair that is being updated. And we update this by taking the convex combination of the previous value plus and the convex combination of the target. And the target has two parts, the immediate reward part plus gamma times the bootstrapping part. Whereas in the bootstrapping part, it's expected SARSA. So we need a target. So the target is just going to be a distribution in this case. So let me define this. So let me just, OK. So distribution over the action. So I just use the letters P. And I'm going to index it with T plus 1 because it's based on the state, ST plus 1. So this is going to be the epsilon, like the probability that the epsilon greedy policy would use if you're at state ST plus 1. And it's epsilon greedy with respect to the current action value function. So how does this look like? It's 1 minus epsilon times the action. OK, put a probability of 1 on the action, which is maximizing the action value at state st plus 1. We don't care about the case when you have ties at the moment. Generally, usually doesn't matter. It's such a fine refinement that we just safely ignore it, assuming that there are no ties. So we put, so this is a probability distribution. This is just the indicator function. It puts a probability mass of 1 on the maximizing action and puts a probability mass of 0 on all of the other actions. And we are mixing this with a weight of 1 minus epsilon with the uniform policy, which puts a probability weight of 1 over a on all the actions. So that's our target. So notice that this depends on qt and st plus 1. And I use the indexing t plus 1 because it's like, OK, that's the most recent time step that we need to have access to data from that time step. And so continuing the update rule, you just have and take all the actions, take their probabilities according to this epsilon greedy target with respect to qt, and compute the average of the action values at the next state st plus 1 with respect to this distribution. And this is the target that we are creating. So this was just expected source, and we have discussed this algorithm a couple of times, right? Questions? All is good. No hidden bumps, typos. All right. So now, how do we make this? How do we merge this algorithm with the idea of double Q learning? So really, the idea of double Q learning was that you keep track, well, you are alternatively and maybe randomizingly are updating one of two action value functions. And in the update equation, if you're updating one of them, then in the update equation, the target, well, maybe the maximizing action, the identity of that maximizing action is computed based on the other action value function. So then the question is, OK, if you want to generalize this to expected SARSA, what do you change? We're going to have two of these action value functions, qt, I. Both of them are mapping from state actions to reals. And the indexing is going to be just use an index of 0 and 1. Then I can write just the expected SARSA equation. And we're going to just for you choose first and index one of the two indices. Usually you choose this uniformly at random. So it's a uniform distribution over the 0 and 1. Just Bernoulli is probably 1/2. So IT is now an index which takes on a value. It's a random index that takes on a value of 0 or 1. And then you can write the update equation for expected SARSA, just copying everything. So that's how I start. Except that I add this index because we have two action value functions. And I have to say which of them is being updated. And only one of them is updated. based on the data that we are processing. Okay. So this is all good, except that I haven't yet specified what PTA should be, PT plus 1A. I just copied the same equation, these minor modifications, but I didn't specify what PT plus 1 is. So now we take the spirit of double Q learning. So in double Q learning, you compute the maximizing action with one of the extra value functions and use the identity of that maximizing action to update the other one. And what corresponds to this is, of course, redefining these probabilities such that here, instead of using QTIT, we're going to use QT, the other IT. So that's 1 minus IT. So PT plus 1A then is going to be just the same thing as what we had before, with the crucial difference that here I'm using 1 minus IT. So this has the property of that, okay, if IT was 0, then I get a 1 here. So it kind of flips the bit. If IT was 1, then I get 0 there. It's just a shorthand notation of like, okay, flip things around. Right? Sounds good? Yes. Put an I here? Oh, this should be IT. Yeah. Yeah. By the way, there could be some variations of this scheme. The same with double Q learning, which kind of mix the target differently. So it's like we're updating IT, but the target is based on 1 minus IT, but the maximizing action is computed based on IT. I don't think that there is any major difference between these. They're kind of the same. At least I don't see a reason of preferring one over the other. This is one very simple way. And it's really in the spirit of what we discussed, that, in these bandits, you're splitting the sample and then use 1/2 of the sample to compute the identity of the maximizing action, use the other half of the sample to get the values. All right. Done. If you know everything about double Q learning, expected SARSA, solving this doesn't take much time. You just write the update equations and then you're good. All right. So I propose that we move on to the very new worksheet. Because I'm excited about it. This is 7. This is 9. All right. Ooh, it's showing you the wrong one. All right. All right. So this week, finally, we got to some really exciting place where we're talking about function approximation used with reinforcement learning. And we'll talk a lot about linear function approximation there. But first, maybe let's discuss this function approximation business. So why do we want to use function approximation in reinforcement learning or machine learning in general? Yeah. Oh, that's a useful property to have if you're using function approximators. It doesn't quite answer why we want to use it. Okay. And that's good for us because why? Okay. Yeah, I think we're getting there. So we can continuously approximate states and actions, whatever that means. Do you want to say something? Right. So model the word based on a fixed amount of data. And when you're talking about a word, you make this gesture, which kind of means that the word is big. Right. Yeah. Yeah. Somehow we have this idea that the word is big. There are lots of states, lots of actions. You can't visit all the states and actions, and you still want to be able to tell how to act if you would encounter a state that you haven't seen so far. And how would that be possible to be intelligent about how to act in the face of a state of the world that we haven't seen yet? Can we do that in general? So imagine a big, big MDP with all these states. And you have seen, just a small part of the state space because you have limited experience. You have so many other states. How can you, it's an extrapolation question, right? From the limited data you have, how can you extrapolate to other states that you haven't seen, that were not in the data? Isn't that magic? Yes, indeed, we can try to fit functions. But the question is going to be, is there going to be any guarantee that when doing this fitting, let's say you're in reinforcement learning, so you need to have a policy at the end. So you do your fitting the best way that you can possibly imagine. And you want to guarantee that the policy that you get out of this is going to work well. And the state was like, the state space was enormous, and you just try this. What's your gut feeling about this? Is this going to work? Yeah. Right. And that is correct. So without any further assumptions about how, like when you're using functional approximation, you're kind of like bringing in some extra beliefs about how you should be extrapolating. But really, extrapolation is just like without further information, it's just not possible, right? Like if you're just thinking about that, there are all these possible states. This state could be good, this state could be bad, but no one taught you, and you haven't seen those states, whether they're good or bad. How would you know how to think about them? So when you're using functional approximation, under the hood, the secret hope is that you kind of chose well the way you're trying to extrapolate. And then the name of the game is going to be, but okay, like if we happen to choose well, can we even do it? Right? Even in that case, it is not immediately clear that you can do this. And to what degree, to what extent you can extrapolate to unseen parts of the state, right? So maybe there are some limits to that. It's really unclear at this stage. Okay, so that about like this whole topic about functional approximation is about this question of, okay, can we design algorithms that are clever enough to use a functional approximator when the function approximator, the use of the function approximator in some really ideal way would give you the right way of extrapolating, right? So maybe, okay, one simple example is linear functional approximation. So what is linear functional approximation? Yeah. Okay, so expand. So you say this is linear regression. What are the components? What are the players there? Okay. Oh, you're thinking about fitting a line? No. I'm just translating to my understanding. I'm not disagreeing. Yes, it's essentially fitting a line. It's a little bit fancier than just line fitting, but just like tiny little bit. There are these features, right? So basically, we have states. They live in, I don't know, anywhere. Like they're just numbers or something, right? But someone might tell you, hey, like this state really looks like this other state. And one way of expressing that is just to assign to them these vectors. So every state gets a vector assigned to it, which we call is the feature vector of that state. And if the vectors are close to each other, then we expect that the two states are going to be close to each other. Or the two states kind of behave identically. That's kind of the expectation in this model. So what do we do with these vectors that are assigned to the states? How do we use them to predict values? So let's say we want to predict values assigned to states. Right. So we take a weight vector and take the inner product of the feature vector and the weight vector. Inner product is just like the sum of, the component products of components. And that's the prediction. It's like really that simple. And it's really just like linear regression. So now you can think about the state themselves are these vectors. So they are this maybe in d-dimensional space, and this is more like line fitting. Okay, so if we are doing linear function approximation, then this assumption that the linear function approximator is going to do well for us, is going to be helpful in extrapolating, what could it mean? What are the possible ways of interpreting this, right? So we kind of agreed that we will need to have something like this, because in the lack of any such extra assumptions that would connect the function approximator with the MDP that you're in, there is nothing that you can do. You can't really extrapolate. So what are some possibilities? How would you want to use linear function approximation to help yourself to discover a good policy, very high level?
You just learned already the weights.
To do what?
So you learn the weights, and now you can like generalize to new states using that, and then you're just kind of like getting the policy from that, right? Like depending on what the weights is being learned in the RL.
So what should the weights do? Give me an example.
Like,
oh, yeah, and the objective is derived from our desire to do what?
you want to maximize the reward at each state, right? Like your value functions.
Okay,
Or maybe
which value function would you want to approximate?
the new states, basically, because
New
they're
states.
assuming you already
Okay.
learn the weights from like I don't know, say like n-1 states,
Right.
and then you want to generalize to like.
Oh, I guess let me rephrase the question. The question is really, at the end of the learning process, you learn a function that assigns values to states, or maybe state action pairs. Doesn't really matter. What do you want this function to represent? The next state is going to be stochastic, right? Because you are in an MDP. Do we care about what the next state is? We really just want a policy. That could be one choice. Try to learn something that right away gives you what would be a good action to choose in states. Yeah. Okay, so I could only hear kind of half of it, but I'm hearing value functions. We might care about some value functions. I would agree with that. That seems like a good idea. Which value function do you want to approximate? The state. The state is the state. Why do we want to approximate it? How does it help? Our goal is to get a good policy. What would you approximate? Maybe that's okay, but I'm not sure I follow. And there is a very simple answer. So if we didn't have a lot of states, what value function would you learn so that you know how to act? You're in the tabular case, back to module 2. Give me some specific value functions that we talked about.
The expected reward, like the full sample, reward GT basically. Right? Instead of like, I guess you're assuming that you have access to the full.
So we can fix a policy and talk about the value function of a fixed policy. We can also talk about the action value function of a fixed policy. We can also talk about some really special value functions, which are really helpful. If we knew them, we would know how to act optimally. What are those value functions? The optimal value function. Yeah. Specifically the optimal action value function, right? Like if I knew the optimal action value function, I would know how to act. So we know that. So maybe one way to think about this is that if only I could use my features to get to the optimal action value function very quickly after only seeing so much data, not seeing all the states, because that's not going to be tractable, then that would be really good, right? So in a way, that could be some ultimate goal, to discover some algorithm that can do that, right? So it's given these features, and it's interacting with an MDP, and the MDP and the features are in harmony. They're not fighting. They like each other in the sense that you can use those features to really get the optimal action value function. Even in that case, it's not obvious that you can get an algorithm that will discover the coefficients, the weights that you need to use to be able to know how to act, that you will be able to use to approximate or like exactly represent the optimal action value function close enough so that your policy that you're reading out from all of this is going to be a good policy. But that's kind of like the whole purpose of this whole module, right? To get to some place like this. And then we can design various algorithms that are trying to do this, and we can think about whether they are achieving this goal. And when do they achieve this goal? Do we need extra assumptions? Or can we just get away with this minimum amount of assumptions that we were discussing so far? All right. So good. So that kind of sets the stage. All right. So back to linear regression. We are using just a linear combination of the features with some weight vector, trying to approximate things, trying to approximate some values. And so if these values are if the problem is defined in terms of input-output examples, where you have the input feature vectors and the target values, that you can just set up a loss minimization problem. Maybe you consider the squared loss, or you could consider some other losses. There are lots of different choices which are interesting, and they have different properties. And then you can look at the weight, which gives you the best such empirical error on the loss against the training data that you had. And this is what you were learning about in machine learning classes, right? And the square loss example is one of the prominent examples. So why do you think the square loss is used a lot? Okay, so one answer is differentiable, and what was the other? What's differentiable? Okay. Anything else? Okay, what is computationally cheap? Okay, so somehow we need derivatives, so gradients, and they're going to be cheap to get. So let's get back to that a little bit later. So one of the reasons maybe is that for the square loss with this linear setup, we can calculate a lot of things analytically. Is that what you're saying? General and not? And not overcomplicated. Okay, so yeah, I don't know what you mean by something being complicated or not. What kind of effort are we talking about? Is it a human effort? Human effort. So, okay, so let's talk about some odd, like, are there any, okay, we'll get back to that too. Some other. Concave or convex? Right, right. It's kind of like, it's weird because this concave convex is like, yeah, like, how do you know which one is which? So when you go in avalanche training, they will tell you that don't ski over concave surfaces, convex surfaces. And by that, they mean that, like, okay, like, that you don't see over it, then, like, you don't go over it. And that's like, there is the Earth, and there is the whole body, and that's a convex thing. And that's just flipped from, in mathematics, you have these functions. They are the other way around. So this shape, x squared, is convex. So just remember that. And then you will never go wrong with anything. X squared is convex. And if you flip it, take negative sign, negative x squared, that's concave. But otherwise, yeah, I also find it very difficult to remember first. Well, okay, after many years of experience, it's okay. Anyways, okay, so convexity is going to be very helpful. And so, yeah, it's convex in what? So what is the loss? I guess maybe I raise this. I don't know what is being recorded when I leave the meeting. This recording may be completely messed up. So why square laws? So first of all, what is this? So we have, am I still echoing? No. We have features which are d-dimensional, weights which are d-dimensional, and we're gonna have responses. And so one data point just looks like this. It's a pair of x and y. It's kind of supervised learning. And the loss on this data point of the weight is just going to be, take the predicted value, which is the net product of w and x, compare it to the target, take the difference, square it, maybe normalize with 1/2. I automatically do that. And so what are y square laws? So one was that L is convex. So L has now many arguments. So which argument are we talking about when we say it's convex? So that's the implication of convexity. So we are taking the gradient with respect to what?
Convex in the input parameter and weight, just because this is like an affine transformation in this sense, because it's just W transpose times X, right?
So it's in W. Yeah. So it's convex in W, right? So for every X and Y, you just look at this as a function of W, and it's a convex function. Okay? L is differentiable. So we like that. What else? There was something about easy, but I would translate that to, and I think that this is one of the reasons people use the squared laws, is because you can do a lot of analytic calculations. The exact minimizer of the empirical loss, you can calculate it. It's like matrix vector products, and like you can just do the calculations. So exact minimizer of empirical loss, easy to, available in closed form. So analytically or closed form, it just means that you can get an algebraic expression. It just gives you the minimum. And that's very helpful if you want to debug things, you know where you want to get to. So here we are talking about this loss, which is just the average. And it's not important that it's the average, just like a good practice to normalize things, of the loss at the individual training examples that you have, W. So if you ask me to give you a minimizer of this, this can be given in closed form as a function of the data. A little calculation gives it, right? What else?
Also, like, I guess we're using the two norms, so like if the outliers are present in the data set, the two norm punishes the outliers more. It depends, I guess, on the use.
Where is the two norm here?
Yeah, I mean, like just like
Is there a two norm here?
the loss function is when you think of it in that way, instead of taking like abstract values, different.
Okay.
So that's just like W.
I don't quite see it, and you were also saying something about outliers. So let me just put outliers here. Okay. And we'll discuss. Did we have any other reasons? Differentiable and the gradient of L with respect to W, of course, is cheap to calculate on a computer. It's like OD. Linear in the number of features. Okay. What's a loss function which is not the squared loss? Oh my gosh, that's beyond what I know. Something simple for this setting. Yeah, absolute value loss. Wow, okay. Yeah. Those are interesting examples. So here is the absolute value. And it is the 0, 1. So sign a loss if these are different. Okay. So call it ops, call it 0, 1, call this just 2. It's very confusing because the R2 is used for other things, but it's fine. You can deal with this ambiguity. All right. So very quickly, we're kind of running out of time. How about L1? Is it convex in W? Okay, a little homework. It's convex. So that takes this. Is it differentiable? It's not differentiable. Is it a big deal it's not differentiable? Why? Okay, I challenged you. You try to use the M1 loss with TensorFlow or PyTorch or favorite package. Is it going to just choke and like say, no, I'm not going to use it?
It basically smoothes it, right? It does a soft constraint.
It's not going to smooth it out. It just takes it, it's going to differentiate it, and it doesn't care about it. It's not differentiable. How many points are there but it's not differentiable? Yeah, it's just one. It's not a big deal. Are you going to ever bump into that point where it's not differentiable? Chances are that you never. And if you bump into that point where it's not differentiable, what do? Like, you can just imagine that, like, there is this kink, and there you just like do whatever. Doesn't matter. Okay, is it cheap to calculate the derivative when it exists? It's very cheap. It's even cheaper, or same cost. Exact minimizer. Is that good? No. We can't do this. How about outliers? Well, you don't know yet, but it's actually better for outliers. 0, 1 loss. Not convex, not differentiable, not exact. Awesome with outliers, but it's in general, in this situation, would be really bad because it always gives you 1, and so you are never happy. So it's not sensitive enough. We see that it's not only the square loss that you can choose other losses. They have different properties, pros and cons. It's a nice topic. In this class, we're going to stick to square laws because it's kind of neat and because of historical reasons, but it's not necessarily the only thing that you want to consider. All right. What? Oh, yeah. Oh, yeah. Sure. You can make it as complicated as you wish. All right. So gradients came up, differentiable came up. You will see a bunch of exercises on the worksheet related to that. And we are going to get back to this next time. All right.